The zero-G docking problem. Kamo-Walewa has a surface gravity so weak that a single human heartbeat generates enough kinetic energy to launch a lander back into deep space. China's Tianwen-2 mission, currently in its cruise phase this May 2026, isn't attempting a landing in the traditional sense. It is attempting a high-velocity mechanical capture of a 40-meter rock that rotates every 28 minutes. This mission is the ultimate stress test for microgravity anchoring tech, and the physics of the attachment mechanism are more complex than the sample return itself. The mission's success depends on one specific mechanical load: 4 arms and counter torque. Traditional touch-and-go sampling used by OSIRIS-REx and Hayabusa 2 relies on momentary contact to kick up dust. Tianwen-2 is doing something different. It uses 4 robotic arms equipped with micropedals to physically grasp the surface while a central drill extracts the core. To maintain stability, the spacecraft must fire its thrusters downward throughout the sampling window to counteract the drill's torque. If the anchor fails to bite into the regolith, the torque will simply spin the spacecraft instead of the drill bit. This isn't just about getting a rock. It's about proving we can hard-mount hardware to a non-cohesive body, and the rotational constraints make the window even tighter. The 28-minute limit. Kamo-Walewa's rotation is a massive constraint. At 1 revolution every 28 minutes, the centripetal acceleration at the equator nearly cancels out the already negligible gravity. This creates a surface environment where dust and pebbles are essentially hovering in a state of precarious equilibrium. Tianwen-2's navigation system has to match this rotation with millimeter-per-second precision to avoid a shearing impact. A mistake of just 5 centimeters per second doesn't just ruin the sample. It likely results in a ricochet that ends the mission. The margin for error is shrinking as we move toward the dual-target phase. The 2-target trajectory gamble. The mission profile includes a 2-part trajectory that many analysts find unnecessarily risky. After sampling the asteroid, the orbiter returns to Earth to drop the capsule, then uses a gravity assist to head toward a main belt comet 311P Pan-STARRS. This requires a hyper-efficient propulsion system and zero margin for error in the initial Kamo-Walewa departure delta V. Critics argue that the dual-target approach compromises the primary sampling mission by limiting the time available for site characterization. However, for the CNSA, the secondary goal of long-term deep space endurance is the actual strategic priority. This shift in focus reveals a deeper objective for the hardware. The real implication. The technical success of Tianwen-2 rests entirely on the transition from passive touch-and-go maneuvers to active mechanical anchoring. While the public focus is on the origins of Kamo-Walewa, the engineering takeaway is the validation of the micro-pedal gripper under drill-induced torque. This specific hardware moves asteroid mining from theoretical papers to a demonstrated capability. By combining the sample return with a secondary comet flyby, China is testing the limits of multi-target navigation and deep space fuel management. If the anchor holds, the barrier to industrial-scale interaction with small-body targets effectively disappears. For those of us tracking mission telemetry, the data point that matters is the force feedback on the 3rd gripper arm during the initial bite. That number will tell us if we are ready to move beyond just visiting asteroids and start manipulating them. Keep an eye on the landing site characterization data expected in late 2026. The specific geological density of the chosen site will determine if the micropedals can actually find purchase. Subscribe for more.